Good day. Today, we are going to discuss about gears.
Gears are tooth members that mesh without slipping to transmit power and or motion between two shafts. A gear is a tooth wheel that engages another tooth mechanism to change speed or the direction of transmitted motion. The smaller one of any pair of gears is known as the pinion, while the larger is known as the gear, regardless of which is driving the other. When the pinion is the driver, the output speed slows while the torque increases, resulting in step-down drive. When the gear is the driver, however, step-up drive occurs in which the output speed increases while the torque drops. In general, gears are utilized for one of the four reasons: to increase or decrease the speed of rotation, to change the amount of force or torque, to move rotational motion to a different axis. One of the functions of gears is to change the rotational direction. For example, power is sent to your car's rear wheels by a shaft that runs down the center of the vehicle, and the differential must turn that power 90 degrees to apply it to the wheels. And lastly, gears is used to reverse the direction of rotation. Gears are included in the wide variety of mechanical devices. They provide a number of critical functions, the most important of which is to reduce the gear ratio in motorized machinery. This is so important because a tiny motor rotating at a high speed can often generate adequate power but not enough torque for a device. An electric screwdriver, for example, has a high gear reduction because it requires a lot of torque to turn screws, but the motor only provides a tiny amount of torque at high speeds. The output speed can be reduced while the torque is raised using a gear reduction. Gears can also be used in automobiles, clocks, weighing scales, household appliances, washing and drying machines, pumps, elevators, and etc. Gears in different industries. Gears act as one of the pillars in many industries including automotive, power plants, aerospace and aircrafts, railways and trains, material handling and transfer systems, marine systems, watering systems, and many more. Classification of gears. The gears can be classified according to the position of shaft axis, the peripheral velocity, the type of gears, and the teeth position. According to the position of shaft axis, gears may be classified according to the relative position of the axis of revolution, and it can be parallel shafts, where the angle between driving and driven shaft is 0 degree, intersecting shafts, where there is some angle between driving and driven shaft, non-intersecting and non-parallel shafts, where the shafts are not coplanar. You will see later the examples of these gears. According to peripheral velocity, the gears can be low velocity type if the peripheral velocity rises in the range of 1 to 3 meters per second, medium velocity type if the peripheral velocity lies in the range of 3 to 15 meters per second, high velocity type if it exceeds 15 meters per second. According to its type, gears can be classified as external, internal, and rack and pinion type. In external gears, the teeth are meshed externally. The bigger one is called gear and the smaller one is called pinion. And in internal gears, the teeth are meshed internally. The annual is the larger one and the smaller one is called pinion. The rack and pinion type is composed of a straight line gear called rack on which a small rotary gear moves called pinion. According to the teeth position, gears can have straight teeth axis that is parallel to the shaft axis, inclined teeth where the teeth axis is at some angle, and curved teeth. Types of gears. There are several types of gears according to its uses. First is the spur gears. Spur gears are used to transfer motion and power from one shaft to another in a mechanical setup. This transference can alter machinery's operating speed, multiply torque, and allow for the final tune control of positioning systems. This design makes them suitable for lower speed operations or operational environments with a higher noise tolerance. Spur gears provide several benefits to industrial applications and processes, including simplicity, which results to a compact design that makes them easy to install even in limited spaces. Constant speed drive. These gears can increase or decrease shaft speed with a high degree of precision at a constant velocity. Reliability. Unlike other power and motion transmission components, spur gears are unlikely to slip during operations. Cost effectiveness. The simplicity of their design also allows for greater manufacturability, making them less expensive to fabricate and purchase even with high specific or customized dimensions. Efficiency. Spur systems have power transmission efficiencies between 95 and 99% and can transfer large amounts of power across multiple gears with minimal power loss. However, spur gears produce noise as the contact occurs over the full face width of the mating teeth instantaneously, and it is not also suitable for application where a direction change is needed. Some of its common industrial applications include transmission, conveyor systems, speed reducers, engines and mechanical transportation systems, gear pumps and motors, machining tools. Helical gears. Helical gears resemble spur gears, but the teeth are cut at an angle rather than parallel to the shaft axis like on spur gears. The angle that the helical gear tooth is on is referred to as the helix angle. It is primarily utilized to reduce speed and increase torque between turning shafts. Helical gears contain special teeth that are placed at a particular angle to the shaft. This leads to more than one tooth being in touch during the function, making the gear capable of tolerating more load. This configuration also allows helical gears to perform quieter and smoother than spur gears because of the load sharing between teeth. However, helical gears are more expensive compared to spur gears. Helical gears are commonly found in automobile or machine tool gearboxes, steam and gas turbines, elevators, conveyors, compressors, and etc. Herringbone. Herringbone, also known as double helical gear, is used for transmitting power between parallel shafts. It was developed to overcome the disadvantage of the high-end thrust that is present with single helical gears. The herringbone gear consists of two sets of gear teeth on the same gear, one right hand and one left hand. Having both hands of gear teeth causes the thrust of one set to cancel out the thrust of the other. Thus, another advantage of this gear type is quiet, smooth operation at higher speeds and do not produce additional axial load. But, same as with helical gear, herringbone gear is also costlier. Some of its applications include heavy machineries and power transmission, high-capacity reduction drives like that of cement mills and crushers. Bevel gears. Bevel gears are used for transmitting power between intersecting shafts. They can operate under high speeds and high loads. The teeth of a bevel gear may be straight or spiral. Straight gear is preferred for peripheral speeds up to 1,000 feet per minute, and the ones that exceed tend to be noisy. A good example of bevel gears is seen as the main mechanism for a hand drill. As the hand of the drill is turned in a vertical direction, the bevel gears change the rotation of the chuck to a horizontal rotation. Spiral bevel gears. Spiral bevel gears are bevel gears with curved tooth lines. They are designed for applications that require high speed and high torque power. Due to higher tooth contact ratio, they are superior to straight bevel gears in efficiency, strength, vibration, and noise. On the other hand, they are more difficult to produce. Also, because the teeth are curved, they cause thrust forces in axial direction. Its main application is in vehicle differential. Vehicle differential is a set of gears that transmit engine power to the wheels, where the direction of drive from the drive shaft must be turned 90 degrees to drive the wheels. Meter gears. Meter gears are identical to bevel gears with the exception that both gears always have the same number of teeth. They provide a steady ratio and are used as important parts of conveyors, elevators, and kilns. However, its gear ratio is always 1:1 and therefore not used when an application calls for a change of speed. Hypoid gears. Hypoid gears are a modification of the spiral bevel gear with the axis offset. The distinguishing feature of hypoid gears is that the shafts of the pinion and ring gear may continue past each other, never having their axes intersecting. The major advantages of the hypoid gear design are that the pinion diameter is increased and it is stronger than a corresponding bevel gear pinion. The increased diameter size of the pinion permits the use of comparatively high gear ratios and is extremely useful for non-intersecting shaft requirements such as automotive applications where the offset permits lowering of the drive shaft. Worm gears. Worm gears are used to transmit power between two shafts that are at right angles to each other and are non-intersecting. Worm gears are special gears that resemble screws and can be used to drive spur gears or helical gears. Worm gearing is essentially a special form of helical gearing in which the teeth have line contact and the axes of driving and driven shafts are usually at right angles and do not intersect. Worm gears have an interesting feature that no other gear set has. The worm can easily turn the gear, but the gear cannot turn the worm. This is because the angle on the worm is so shallow that when the gear tries to spin it, the friction between the gear and the worm holds the worm in place. This feature is useful for machines such as conveyor systems, in which the locking feature can act as a brake for the conveyor when the motor is not turning. Worm gear is always used as the input gear, and the torque is applied to the input end of the worm shaft by driven sprocket or electric motor. But worm gears yield low efficiency because of high sliding velocities across the teeth, thereby causing high friction losses. Rack and pinion gears. The rack is a bar with a profile of the gear of infinite diameter, and when used with a meshing pinion, enables for converting rotary motion into linear motion or vice versa. The rack and pinion steering system, which was used on many cars in the past, is the most well-known application of a rack. The gear that engages the rack is rotated by the steering wheel of a car. When the gear spins, the rack moves right or left, depending on which way we turn the wheel. A rack and pinion mechanism also drives the wipers on a car's windshield. Internal gears. Power is transferred between two parallel shafts using internal gears. An annular wheel with teeth on the inner perimeter is used in these gears. As a result, the drive is very compact. The meshing pinion and annular gear run in the same direction in these drives. Internal gear allows compact design since the center distance is less than for external gears. It is used in planetary gears to produce large reduction ratios, in cement mill reduction gearboxes, gear couplings, and etc. Gear ratio. Gear ratio is the ratio between the rotational speeds of two meshing gears. It is calculated by dividing the output speed by the input speed or by dividing the number of teeth of the driving gear by the number of teeth of the driven gear. When mated gears are of different sizes, the resultant output torque and rotational speed are affected as the gear ratio is not equal to 1. For example, the driving gear has 10 teeth while the driven gear has 20 teeth. In order to find the gear ratio, we just need to divide the driven gear by the driving gear. In this case, the answer is 2 to 1. This means that every revolution of the driving gear will cause the driven gear to revolve through only half a turn. Thus, if the engine is operating at 2000 revolutions per minute, the speed of the driven gear will only be 1000 revolutions per minute since the speed ratio is then 2 to 1. This arrangement doubles the torque on the shaft of the driven unit. The speed of the driven unit, however, is only half that of the engine. Depending on which of the driving and driven gear is the larger and which is the smaller, and consequently which has more teeth and which has less, the resultant gear ratio can produce output speed and torque which are increased or reduced with respect to the input speed and torque. Additionally, as there is an inverse relationship between the two values, either speed can be increased or torque can be increased, but not both. A higher gear ratio equates to high torque and lower speed, while lower gear ratio associates to low torque and higher speed.
Parts of the gears. Referring to the picture on the right, outside diameter is the diameter of a circle around the outer surface or topmost part of the gear tooth, while pitch diameter is the diameter of the pitch circle. The pitch circle is the imaginary circle found at the point where the teeth of two gears mesh. Root is the bottom part of a gear tooth spaces, and root diameter is the diameter of a circle around the bottom or root of the gear tooth spaces. Gear is the larger of two interacting gears or a gear on its own, and pinion is the smaller of two interacting gears. Base circle is the circle from which the involute portion of the tooth profile is generated. Most modern gears use a special tooth profile called an involute. This profile has the very important property of maintaining a constant speed ratio between the two gears. The involute profile is the path traced by a point on a line as the line rolls without slipping on the circumference of a circle. It may also be defined as a path traced by the end of a string which is originally wrapped on a circle when the string is unwrapped from the circle. Pitch circle. When gear sets are visualized as a pair of smooth contacting discs, the pitch circles of the gears correspond to the diameters of the discs. Pitch circles of mating gears are tangent to each other and have identical linear velocities. For that reason, pitch circles rather than base circles are used in many gear calculations. The operating pitch circles will respond to any variations in center distance of the pair by enlarging or contracting. Diametral pitch is a measure of tooth size and equals the number of teeth on a gear divided by the pitch diameter in inches. A large diametral pitch ratio indicates a small tooth, and vice versa. The use of diametral pitch is a handy reference in gear design, and a standardized code has been established to facilitate the specification process. It's important to note that meshing gears must have the same diametral pitch. Circular pitch is the distance along the pitch circle from a point on one gear tooth to the same point on an adjacent gear tooth. Calculated in inches, the circular pitch is equals the pitch circle circumference divided by the number of teeth. Because circular pitch is directly proportional to module and inversely proportional to diametral pitch, meshing teeth must have the same circular pitch. Module is the metric equivalent of diametral pitch. That is, the pitch diameter in millimeters divided by the number of teeth. But unlike diametral pitch, the higher the number, the larger the teeth. Meshing gears must have the same module. Pitch point is the point where gear teeth actually make contact with each other as they rotate. The pitch point always lies at the line connecting the centers of two gears. Center distance is the distance between the centers of the shaft of one spur gear to the center of the shaft of the other spur gear. The standard center distance between two spur gears is one-half the sum of their pitch diameters. Pressure angle is the slope of the tooth at the pitch circle. Examples: the center distance of a 4-inch pitch diameter gear running with a 2-inch pitch diameter pinion is 3 inches. To get the center distance, we must add the pitch diameters, which is 4 inches, and 2 inches, and divide it by 2, which results to a center distance of 3 inches. A gear has 18 teeth and a diametral pitch of 8. What is its pitch diameter? Since the formula of pitch diameter is dividing the number of teeth by the diametral pitch, which is equals to 18 divided by 8, the result would be 2.25 or 2 and 1/4. A gear has a pitch diameter of 3.125 and a diametral pitch of 8. How many teeth does it have? Substituting the given measurements of the pitch diameter and diametral pitch, we get the result of 25 teeth. Calculate the center-to-center spacing for the two gears specified below. We first calculate the pitch diameter for each of the two gears. Substituting the given to the equation, the pitch diameter of gear 1 is 1.5 inches and in gear 2 is 2.5 inches. Obtain center-to-center distance by adding the two diameters and divide it by 2. Substitute the resulted diameters of the two gears. The center-to-center distance is 2 inches. The number of gear teeth is the diametral pitch multiplied by the pitch circle diameter. Tooth size is a ratio which determine the number of teeth in a gear for a given pitch diameter. Diametral pitch, module, and circular pitch are all indications of tooth size. In designing a gear set, the number of teeth in each member is of necessity. As a rule of thumb, teeth should be large and low in number for heavily loaded gears, and small and numerous for smooth operation. Addendum is the distance from the top of the tooth to the pitch circle. Its value is equal to 1 module, while the dendum is the distance from the pitch circle to the bottom of the tooth space, or root circle. It is bigger than addendum and is equals to the addendum plus the working clearance. Addendum circle is a circle bounding the ends of the teeth in a right section of the gear. The addendum circle is the circle bounding the spaces between the teeth in a right section of the gear. Hole depth is the total depth of the space between adjacent teeth and is equal to addendum plus the dendum, also equal to the working depth plus clearance. Working depth is the depth of engagement of two gears, that is, the sum of their addendums. Working clearance is a radial distance from the tip of a tooth to the bottom of a mating tooth space when the teeth are symmetrically engaged. This margin compensates for the thermal expansion that occurs during operation and prevents the top of a gear tooth from interfering with the root of its mating gear tooth. Its standard value is 0.157 meter. Tip and root clearance is the distance between tooth root and the tooth tip of mating gears. Face width is the length of the teeth in the axial direction. Space width or tooth space is the arc distance between two adjacent teeth measured on the pitch circle. Flank of the tooth is part of the tooth surface which is lying below the pitch surface. Tooth form depths. There are several tooth form depth options for involute gearing in common usage, with the full depth design being the current standard because of its balance of strength and smoothness. Other involute options include modified, long and short, addendum teeth, and the obsolete stub tooth. Line of action is the path of action for involute gears. It is the straight line passing through the pitch point and tangent to both base circles. Point of contact is any point at which two tooth profiles touch each other. Path of action is the locus of successive contact points between a pair of gear teeth during the phase of engagement. Pressure angle is the leaning angle of a gear tooth, an element determining the tooth profile. Recently, the pressure angle is usually set to 20 degrees, a good compromise for power and smoothness. In general, higher pressure angles provide higher strengths and a lower tendency to experience tooth tip interference, but are susceptible to noise and higher bearing loads. Low pressure angles are quieter and smoother, have lower bearing loads and lower frictional forces, but are susceptible to undercutting at low number of teeth. It is important to note that meshing gears must have the same pressure angles. Tooth. Tooth thickness is the width of the tooth measured on the pitch circle. Backlash is the difference between the space width and the tooth thickness. Standard gears are designed with a specified amount of backlash to prevent noise and excessive friction and heating of the gear teeth. Backlash is achieved either by decreasing tooth thickness slightly or increasing tooth space on one or both members, or by increasing center distance between gears. This prevents binding and compensates for the effects of thermal expansion, machining, and installation variation. List of formulas. Here are the list of some formulas that can be used to solve the parts of the gears.